Suppose that a neutron travels from a location r to a position r plus delta r omega hat in delta t seconds. Also call delta A the unit area normal to delta r such that during delta t the neutron travels through a volume element defined by delta r times delta A. In general, we know that the change in the number of neutrons per unit time is equal to our sources of neutrons minus the losses of neutrons. Inside of a given volume element, delta V, for a time period delta t, the change in the neutron density of the volume element is the neutron number density at time t plus delta t minus the neutron number density at time t multiplied by the volume element delta V. For the moment, we'll hold off on picking apart the different sources of neutrons in the system. Let's just call the source of neutrons some function s times the volume element times the time period. On the other hand, neutrons can be removed from a particular energy, direction, and volume region through two primary mechanisms. First, the neutrons may stream out of the volume element. In this case, the neutron exits from the surface of delta V. This can happen even if the neutron maintains the same energy E and direction omega hat. Secondly, the neutron can interact or collide with the material. In such collisions, the neutron will almost certainly change either its energy or direction. Note that when a neutron collides with a target nucleus, it doesn't necessarily leave the volume element. Neutrons streaming through a volume element travel with a speed v of e in the delta r omega hat direction. Therefore, the streaming losses are denoted as the neutron number density at a position r plus delta r omega hat minus the neutron number density at position r multiplied by the neutron velocity v of e times the surface area normal delta A times the time period delta t. Whether or not a neutron interacts with the material is based on its total cross-section. Therefore, the collision losses are the total cross-section multiplied by the neutron number density times the velocity times the volume element times the time period. Putting all of this together, we see that the change in the neutron number density is equal to the source term minus our two loss terms. We can then divide this entire expression by our volume element and our time period. Recall that the angular flux psi is equal to the neutron number density times the velocity. Therefore, we can substitute this value in our expression below. In the limit where the size of the volume element goes to 0 and the time period also goes to 0, our difference equation becomes a differential equation as we replace the deltas with derivatives. Note here how the area normal to the direction of travel, delta A, has completely dropped out of this expression. Because dr represents the change in position along the direction of travel of the neutron, ddr is the derivative with respect to the direction of travel. More generally, this can be written as the direction of travel dotted by the gradient, or ddr equals omega hat dot the gradient. Thus, the differential equation becomes 1 over the speed times d of the angular flux dt equals our sources of neutrons minus omega hat dot the gradient of the angular flux minus the total cross-section times the angular flux. This is the neutron transport equation in its basic form.